Hi, today we're going to deal with CMOS conduction complements. So we're going to start off with the theory around this topic. Then we're going to go into pull-up circuits. And I'm going to show you all how do we build pull-up circuits. How do we arrange the CMOS gates. Then we're going to go into pull-along circuits. How do we use the pull-up circuit and the expression for the pull-up circuit to derive the expression for the pull-along circuit. And how we translate that expression into a pull-along circuit. And then we're going to combine the two circuits to show the complete circuit that caters for both ones and zeros. So let's begin. So there are some rules that apply when we come to CMOS conduction complements. I want to bring two of them to your attention. So the first is when we have two NMOS transistors in parallel, basically what we have is an OR expression. So in this case we have A and B, A being channel to one of the NMOS transistors and B being channel to the other. The overall expression would be A or B. Now if you have those two NMOS transistors in series, it indicates an AND expression. So as a result, in this case, this network will result in an overall expression A and B. Now let's say we have two PMOS transistors in parallel like this. The expression would be A prime or A bar or B prime or B bar. That's the expression for that parallel network of two PMOS transistors. If we have those two PMOS transistors in series, our overall expression would be A prime and B prime, or if we use bars, A bar and B bar. So that's generally how it works. If you have a circuit consisting of NMOS and PMOS transistors, you have to look at which transistors are in series, which ones are in parallel, and you could come up with the expression for the network. So what about if I give you a pull-up circuit, right? I give you a pull-up circuit and I tell you, come up with the expression for the output F for that pull-up circuit. And also now, how do we now utilize that pull-up circuit to come up with the pull-along circuit? So we're going to start off with exploring this given pull-up circuit and come up with the expression for the output F. So let's do it. Okay, so this is a given pull-up circuit. This pull-up circuit consists of a parallel network, two PMOS transistors, one connected to A, one connected to C. And this parallel network is in series with B, which is connected to another PMOS transistor. And that channels to the output F. Now some back information, a pull-up network, right? The pull-up circuit is responsible for pulling F to VCC or logic 1 if that scenario arrives. So if the logic suggests that if A, the result of this parallel network in series with this B should result in a logic 1, this pull-up circuit will allow for a clear path of F to VCC. and hence F will be pulled up to VCC. So therefore F will be a logic 1. So if we required to find the expression of output F for a pull-up circuit, is very simple. You have to first look at which parts of that pull-up circuit constitute a parallel network and which constitute a series network. So let's look back at the circuit before we move forward. Basically, that pull-up circuit contains a parallel network, and that parallel network is in series with this component here. So let's use that to our advantage. First part, let's get the expression of the parallel network. Right, this network here, that is two PMOS transistors in parallel. So therefore the expression when you have a PMOS transistor, this A becomes A complement, the C becomes C complement, and because they are parallel network, they will be all together. So therefore the expression for that network is A complement or A prime or C prime or C complement. Anyone you could use, C prime, prime, complement, or bar. Same thing. So we're going to be using complement, bar, and prime interchangeably. So that expression is A prime or C prime. And that network is in series with the last PMOS transistor, which is connected to B. Right? That parallel network is in series with this PMOS transistor. So therefore, in series, it means we're going to AND the expression for this parallel network with the expression resulting from this PMOS transistor. And when we do that, we end up with A prime or C prime in brackets and B prime. That's the expression for output F for the pull-up circuit. So now we have the expression for F. What about if we were asked to come up with the expression for the pull-on circuit for the right? So the expression for F for the pull-on circuit. How do we do that? So we can now utilize that expression for output F for the pull-up circuit to come up with the expression for output F for the pull-on circuit. Some background information: the pull-on circuit is responsible for the logic zeros on the output of output F. So like the pull-up circuit, which will pull F to VCC so that you get your logic 1s, the pull-on circuit is responsible for pulling output F to ground so that you could actually now have F taking values of 0. If there is no pull-on circuit, then output F will never be logic 0, and in those cases it will be undefined. Likewise, in the pull-up circuit, if there's no pull-up circuit, then output F will never be connected to VCC. It will never be logic 1, and therefore it will be undefined in those cases when it was supposed to be logic 1. So to get the expression for the logic output F, to get the expression for output F for the pull-along circuit, we actually apply duality. This means that complemented, we're going to actually invert the variables. If they were A prime, they will now be A. Alright, so if they were complemented, they will now not be complemented. ANDs will be turned to ORs, or ORs will be turned to ANDs. Right? So AND expressions turn to OR expressions, OR expressions turn to AND expressions, and we invert the variables. So therefore, A prime or C prime in brackets dot B prime equals, first thing we do, we invert all those A prime, C prime, B prime, so that now they are A, B, A, C, B. The ORs are turned to ANDs, the dot. ANDs are turned to ORs. So our expression becomes A and C all or B. Now we could use that expression now, this expression here, to determine, to draw the pull-along circuitry. This expression indicates that we have A and C. So therefore, we have A and C. We have basically, and one thing to keep in mind, whenever we have complements or complements in our expression, it indicates that we have PMOS gates. When we have no complements, then it indicates it's NMOS gates. So therefore, we have a circuit that we expect will only have NMOS gates. Now, this A and C means that we have two NMOS transistors in series. One connected to A and one connected to C. That's here. Right? Two NMOS transistors in series. One connected to A and one connected to C. And this expression is ordered to B. That indicates that we have another NMOS transistor, but that NMOS transistor is in parallel with the network of NMOS transistors that are connected to A and C. So these two that are in series, they are in parallel with this NMOS transistor that is connected to B. And that is how we get the pull-along circuitry. We must connect it to ground at the base, and F is connected to the top, right? Now that we have both the pull-up and pull-along circuit, what about we combine them together to give the complete circuit that caters for both logic 1s and logic 0s. So this is the complete circuit that produces logic 1s and 0s on output F. If you notice, this circuit has both circuitries. It has the pull-up circuit, which is connected between F and VCC, which is 3.3 volts. And that's the upper half. And it also has the pull-along circuit, which is connected between ground and F, the lower half. So basically, whenever we have a scenario that results in a logic 1 being assigned to F, is because we will see F equals to logic 1 because the logic suggests, it gives us a clear path to channel F, connect F to VCC, pull F up. So this pull-up circuit is going to pull F to VCC so that we now have F equal to logic 1. And in the case where we have a logic 0 for 0, it is because this circuitry, pull-along circuitry, pulls F to ground so that we now have F being equal to logic 0. The two circuits, pull-up and pull-along, are needed. Anytime any of them are missing, for instance, if the pull-up circuit is missing, then instead of logic 1s, we will have undefined. And if the pull-down circuit is missing, instead of logic 0, we would have undefined at the output F, right? So if you had to create a truth table for the pull-up circuit, it would be on the output, it would be logic 1s and undefined for when there is the logic 0 cases. Since there isn't a pull-down circuit in the pull-up circuit, then we would have undefined. And if we was to do the truth table for F, for the pull-down circuit, we would have undefined for the logic 1 cases, and we'll have zeros for the 0 cases. And that was very easy. One thing I want to remind you is that if any of these circuits, the pull-up or pull-down circuits, are missing, any of them missing from the complete circuit, then the logic on the output F that they are responsible for will not be possible. So for instance, the pull-up circuit is responsible for logic 1s. We spoke about that. If there is no pull-up circuit, then there is no logic 1s on the output F. And what's going to be on the output F in the cases that you're supposed to have logic 1s, you're going to have undefined. Similarly, the pull-down circuit, if there's no pull-down circuit, then we cannot have the output F being pulled to 0. So therefore, it's going to be undefined for those cases also. So it's very important to have both a pull-up and pull-down circuit in your entire IC. Right? Your IC system must have a pull-up and pull-down circuit. They need that. So I hope this was very informative. I hope you understood it, and I'll see you all on the next one.